Hey guys, this video is trying to explain question 4 from the practice questions for Math 3274. Practice final exam questions. Okay, and what does the question say? Oh, we have a topological space X, and we have two subsets of X, and we are supposed to prove that the union of the closure of A and B, the closure of the union is the union of the closure. Okay, let me just remind you what the closure is. So if I have a subset U, the closure of U is U bar, which is all the elements of X, such that whenever you have an open set containing X, that open set intersects U. And here's my picture. Here's my set V. Here's my set U, this blob, and this X. And whenever I draw a circle, that's supposed to represent an open set. Whenever I draw a circle around X, I cannot help but include some elements of U. That's what it means to be in the closure. Here I have another example. Here's my blob. My set U is this blob. And here I have an open set containing X which does not intersect U. So this X is not in the closure because there exists a open set which does not intersect U but does contain X. Okay. So let's try and prove this equality. Okay, so what do we do? Let X be in the closure of A union B. And what does that mean? And for all V in T such that X is in V, we have V intersect A union B is non-empty. Okay, that's a good place to start. Okay. Now we want to show that either for all V such as X and V, either we want to prove like V intersect A is non-empty for all V or something like that. So let's suppose that V intersect A is empty for some V. Okay, so if for all V in T such that X is in V, we have V intersect A is non-empty, then we're done. Then X is actually in the closure of A. And that's kind of what we want to show, that X is either in the closure of A or at the closure of B. Okay, so let's suppose that this is not true. That there exists V in T, let's call it V0, such that X is in V, V0, and V0 intersect A, is empty. Okay. Okay, now let's take let's take an arbitrary open set. Let's call it, well, I don't want to use V anymore. Let's say U. And let's assume X is in U. And we want to show that U intersect B is non-empty. Okay. I guess we might as well do this by, I mean, let's just do it by a contradiction. Why not? Suppose that U intersect B was empty. This will be a problem. So see if you can think of why that might be a problem. Maybe I'll draw a picture. This is U. This is V. Here's X. Okay. Now U does not intersect B. So maybe I need a different color to draw. Let me draw B. Oops. Sorry. Here's B. And I need a different color for A. A is going to be yellow. A doesn't intersect with V. So A, this is A. Okay, but now notice U intersect V does not intersect A union B. This is A. And that is our contradiction because U intersect V is an open set containing X, which doesn't intersect A union B. Okay, so that is our contradiction. Well, we just have to somehow translate this kind of picture into an actual proof. So this is for a contradiction. So it's a symbol for contradiction. Okay. Then X is in U intersect V0. U intersect V0 is an element of T because the intersection of two open sets is still open. That's one of the properties of a topology. Okay. So X is in U intersect V0. U intersect V0 is an open set. But U intersect V0 intersect A union B is empty. Right? How do we argue that? Well, I guess you might just think about this diagram. That's good enough. Okay, and therefore X is not in the closure of A union B, and that is a contradiction. Okay, so therefore, what is it a contradiction to? Well, whatever U, open set U which contains X, we must have U intersect B is non-empty. Therefore, X is in B closure. Therefore, the closure of A union B is contained in the closure of A union the closure of B. Now we have to do the other side. Well, for the other side, we have to show that it's enough to show that the closure of A is contained in the closure of A union B, and the closure of B is contained in the closure of A union B. Okay, so let X be in the closure of A, let V be an open set such that X is in V. Now, since X is in the closure of A, we have V intersect A is non-empty. Well, then V intersect A union B is non-empty. Therefore, X is in the closure of A union B. And the exact same argument with B's instead of A's tells you that the closure of B is contained in A union, closure of A union B. Oops. And similarly, closure of B is contained in, oh boy. I just want to write absolute values for some reason. There we go. Now, if two sets are contained in a set, then their union is. So we conclude that this, we have the union of the closures is contained in the closure of the union, and then we've done both sides, so finally they're the same. Okay, the end.